All right, we're back for part 2 of our gases unit and our preparation for the AP chemistry exam. I want to take a few moments and go over what's called the kinetic molecular theory. And I realized in class I told you guys something that was slightly off the other day, but we want to go ahead and correct it. Make sure you have the ideas of why we believe gases behave the way that they do. These are the assumptions that we're able to take. Now, this is usually backed up by math, so it's not just random assumptions like a person who has no idea, but based on the things that we have observed, we're able to make these assumptions. First, that gases are composed of tiny particles traveling around in random straight line motion. We can do a demonstration of this so you're able to see exactly what I mean by this. Two, the volume of the gas particles is negligible compared to the overall total of the volume. We talked about that before with taking about a 0.1% of the actual container. Three, the attractive and repulsive forces between particles are negligible. Because of the fact that they're moving as fast as they are, we don't expect the attractive or repulsive forces to have enough time to kick in. Collisions are perfectly elastic, or the total kinetic energy of the gas before and after the collision is the same. No real energy was transferred. They're moving at about the same pace. And that the average kinetic energy is proportional to the absolute temperature of the gas, meaning the kinetic energy is based on how much heat is available there within the system. So if I make the temperature to go up, then the energy of the gas should also go up. If I bring it down, the energy of the gas will also decrease. This is given to us to show a little bit of an explanation of what happens at each temperature in terms of our molecules, what happens with the speed using just a regular plot. And we notice that as we raise the temperature, the average speed and the molecules that reach that speed increase, or the fraction of the molecules increase. What does this mean? That one, not all molecules have the same speed within the sample of a gas. Two, the higher the temperature of the sample, the higher the average speed. Higher temperatures cause higher kinetic energy because the molecules increase. We have molecules increase. Using our kinetic energy formula, we can sort of explain this. Higher temperature will always also cause higher pressures, and larger volumes of gas will have less pressure at a given temperature, since there will be less collisions with the walls, the containers. Now, using a similar information, but now you're looking at a Boltzmann distribution, we're able to see also what happens in terms of the size of the particles and how that affects their average speed. Starting with one that might be heavier in terms of oxygen, even at the current temperature, more of the particles are moving much slower, whereas at the same temperature, helium, being much lighter, or even hydrogen gas, is moving much faster for a longer period of time with less energy output from other conclusions. And this is just rehashing those same points. Now, diffusion. We've all dealt with diffusion from probably second grade on. But the idea is, how fast do gas particles spread within a given space? This would be a large space. So if I was to spray some cologne in the front corner of my class, how long would it take to reach the back corner of my class? And I could determine the diffusion rate based on those things. Smaller molecules, of course, are going to move faster. Graham's law. Now, effusion is very much like diffusion, but the difference is we're looking at how much time does it take for gas to go through or to leave through a smaller opening. The example given, we have a balloon that deflates over time. The gas particles don't all rush out at the same time. Depending on the size of the hole, they usually take a lot longer if it's very small. Now, consider we have two gases in play in this. We'll say that there's an inverse relationship, inverse relationship for our rate 1 over rate 2 is equal to the square root of the molar mass of our second gas over our molar mass of our first gas. They're going to have a different ratio. Depending on how I continue to go through this, we're able to see, let me just use this example to make it a little bit clearer. We have helium gas, which has a very, very small molar mass compared to nitrogen. If we were to place these molar masses in this ratio, we will be able to see that the square root of 28 divided by the square root of 4, we get a value of 2.6 times faster in terms of effusion. So helium would go out almost 3 times as fast just because the particles are smaller, and they would be able to make it through a lot quicker than would our nitrogen molecules. Now, real and ideal gases. For the ideal gas equation, or the ideal gas law, we look at the ratio between pressure and volume divided by our R value, our universal gas constant, times the temperature. And we say that from this we can determine how many moles of gas are present. Now, for a real gas, when we make even small changes, it makes a huge difference in the number of moles that could be there. Because smaller distance between gas molecules, more likely attractive forces will actually be able to develop. So when I change the volume, there's a better chance that I'm going to have those attractive forces to take place. The real gas, or what we call as a real gas, it does not resemble as much what we would want to happen, or an ideal situation. So when the temperature decreases, they move slower, closer together, more intermolecular forces can can form, including our London dispersion forces. So what do we want to happen? We want to make sure that these particles are consistently, one, moving, but also that as they're moving, they have the temperature and the pressure remain at a level where they will remain in gas form. This is what we mean by an ideal gas. So we no longer take into account the particle size, and we want to keep them at a temperature where we would not have to worry about them interacting or becoming liquid or even solid if the temperature decreases as such. And this is another example of what we're saying at certain temperature and pressure. In this case, we're looking at the temperature. An ideal gas will remain the same constantly. But as we deal more and more with the real gases, we notice that we get the drop in the relationship between temperature and pressure. Now, conclusion, and this is where we wrap it up. If you want your gas to behave more like an ideal gas, we'll keep the temperature high and the pressure low. This will allow them the space that they need and the ability to move about and lessen the chance that they're actually going to turn back into a liquid. This is going to be it, and I will see you all in class. Don't worry, there are many examples to come, and I look forward to seeing you in class. Have a great afternoon.